Hi everyone, my name is Srichandra and today my topic is a novel zero-one deadlock detection methodology for multi-unit resource system and its hardware implementation for system on chip. Let's get into the topic. Introduction. System on chip and chip multiprocessor are new concepts featuring the design of single chip containing processor cores in addition to local memory and other intellectual property cores. Such design paradigms are suitable for not only embedded systems but also high performance systems and provide the balance among cost, power consumption, and performance. Recent technology enabling to integrate a tremendous number of transistors has allowed multiple processors to be fabricated on a single chip. In fact, the world is in an early stage of proliferation of CMPs for scientists and embedded computing domains, as well as the general purpose computing domain. For example, the Cell Broadband Engine CBE is an 8-core heterogeneous CMP developed by IBM, Sony, and Toshiba. CBE-based embedded systems are in, envisioned on promising solutions for high-speed media processing systems and medical system. The transistor counts continue to increase and in all likelihood follow Moore's law. Multiprocessor system on chip MPSO series are very likely to become more prevalent in the nearly future. Background with definitions. In the section, we introduce some concepts from graph theory and operating system, which play important roles in our algorithm. Above all, we use a RAG to represent the resource allocation scenario among processes and resources in a system. A RAG is defined as a graph V, I, where V is a set of nodes and E is a set of directed edges. We can be further partitioned into two disjoint subsets, processes set P and resource set P. A RAG is bipartite graph in these two sets, meaning no edge between two nodes, both in the same set P or Q. A new deadlock detection methodology for multi-unit resource system. In this section, we first present some assumptions for a target system. Then we describe a matrix representation for a weighted RAG on which our hardware algorithm is based. Next, the details of our deadlock detection algorithm for multi-unit resource system are presented and steps through with an example. Assumptions for the presented deadlock detection algorithm. We make the following assumptions for its applicable system. Each type of resource has been fixed on total number of units. The system is in an expanded state. A process requests one resource unit of time, single unit request system. Thus, a process is blocked as soon as it requests an unavailable unit of resource. By theorem 4.1, a not becomes a necessary and sufficient condition of a deadlock. The theory behind deadlock detection in multi-unit resource system. In this section, we introduce two necessary and sufficient conditions for deadlock with respect to a RAG. It is well known that a cycle in a RAG is a necessary and sufficient condition for deadlock for single unit resource system. However, in multi-unit resource system, cycle in a RAG is no longer a sufficient condition for deadlock. The following theorem introduces a necessary and sufficient condition for a deadlock in a multi-unit resource system. Introduction of a matrix representation for a weighted RAG. Commonly, a graph is represented by an adjacent matrix. For specifically, a RAG can be represented by an m plus n into m plus n matrix, where m is the number of processes and n is the number of resources. Each element of the matrix is either 1 or 0, with 1 indicating an edge directed from the node labeled by the row to an node labeled by the column, and 0 indicating no edge, such as adjacent matrix for a RAG is defined as following. Due to the bipartite property of a RAG, if we arrange the nodes such the process and resource nodes appears consecutively among rows. The column in the matrix, we obtain two zero submatrices and the other two non-zero ones, as shown in the figure 5. Therefore, it is sufficient to use only the two non-zero submatrices to represent a complete RAG on one denoted as in AG in figure 5, representing grand edges, and the other denoted as AR, representing request edges. According to assumption 3, for each process node in the rank, there can exist at one outstanding request edge. Therefore, each row in the sub-adjacent matrix AR can contain at most one non-zero value. If a process has no pending request, then its node in the RAG has no outgoing edges, and its corresponding rows in the matrix has all zero values, such as process nodes is a sink in the RAG. A sink node represents an active process because the process has acquired all necessary resources to run our algorithm and its detail. Before we present the parallel MDDA, let us first introduce and explain some data structures used in the algorithm as shown in the table 1. These data structures include 7 matrices and 2 vectors among the data structures. A set of matrices AG, AR and weights, as well as set of vectors free unit and sync process, are used to store information representing a weight RAG. A set of matrices sync, work process, work resource, and previous resource are used to store information on such search results during the intermediate steps of MDDA. In this article, matrix I, and matrix J refers to as all elements in the matrix. All elements of row J in the matrix and all elements of column J in the matrix respectively. Two sub-adjacent matrices A, G, and AR for a RAG, a weight matrix weights, a free unit vector. Free unit have been defined in free unit allows to algorithm to decide whether a request can be granted or should be blocked. Sync process vector allows the algorithm to immediately know whether or not a reached process node is a sync node during the search of reachable sync nodes. Sync process can be defined as follows. The matrices mentioned so far always maintain their states, whereas the following 4 matrices are initialized every time. Step 4 for algorithm 4.5, that is MDDA, is entered a sync ID matrix sync, store information about all sync nodes for each and every resource. Nodes, and it's used to detect deadlock in a constant runtime. A sync ID in matrix. Hardware implementation. In this section, we delineate how algorithm is realized in hardware. The algorithm has been implemented using Verilog HDL architecture of the MDDU. The simplified view of the architecture of an MDDU for 3 processes and 3 resources issued in figure 9. The architecture consists of matrix cells, SK or W cells, WR or PR cells, SP cells, free unit cells, and a decision cell in addition to finite state machine cells, FSM cell in short. In this following, we describe the architecture in detail. Matrix cells, free unit cell, and SP cell. The matrix cells of the ith row and jth row, denoted as matrix cells, contains 3 registers where the register which stores the value of AR, AG and weights. All the MN matrix cells together stores the complete resource allocation picture in the system. The contents of these cells are not altered during the computations of MDDA. Their contents can only be changed by the operating system when the resource allocation situation changes. Each 3 unit cell contains the value of the number of 3 units for each resource. When a unit of resource J is granted to process Pi, the value of AG in the matrix cell is set to 1. The weight register in the same cell is necessarily by 1. In addition, the value in the free unit cell of jth row is reduced by 1 when the request from process pi for resource gi is blocked, only the value of ar in the matrix cell is set to 1, and all other register values do not change. For the case where unit of resource gi held by processor pi is released, the weight register is matrix cell is decreased by 1, and the value in the free unit cell on the jth row is increased by 1. Information about whether or not a process node in is a sync node in the RAG is stored in the SP cell. Each SP cell contains the value of an element in the vector sync processor, which is computed by performing bitwise or operations among the elements of AR. That is the AR output of matrix cells on the ith row, as it described in I1. Conclusion. The described algorithm is designed to be fully hardware orientation and exploits the maximum computational parallelism in hardware for detection preparation. The algorithm has a runtime completion of 0 of 1 for detecting deadlock and 0 minimum for preparing detection. Second, we discuss the implementation of MDDA in hardware in detail. The MDDU provides very fast and deterministic runtime detection of deadlocks for both multi-unit as well as single-unit resource system. It is especially beneficial for MPSOC, which we predict will prevail on as embedded systems platform. The MDDU stores the RAG of a system in a set of matrices. Whenever a resource request is blocked, the MDDU makes deadlock decision right away by comparing the information on the reachable sync processes of the requested source with the ID of the requested process. Thank you.